All right, hello everybody. Welcome to Math 6310. My name is Chance Glenn. I am your instructor for this semester. I'm also the provost, so that means I'm the academic leader of the university. So if you have issues on any academics, you also can talk to me. So that's a little extra perk. If you don't like the way this class is taught, then you could come to me and complain about it, and I'll get on me about it. All right? Anyway, this is Chaos and Fractal Dynamic Systems. That's the name of the course. And what we'll be doing this semester is really just trying to explore some of the basic concepts and some introductory concepts, and we may get a little bit deep in some areas, but this is going to be about learning this course, having fun, understanding it. What is chaos theory all about? What is fractal geometry all about? That's what we're going to be exploring this semester. So let's just talk about class a little bit, and what I'm going to do now is I'll pull up the syllabus. This should be available to you in Blackboard, and you'll be able to see. We don't have a textbook per se, but I do have some books that we would be using for reading assignments that you'll see as we get down a little further in the schedule. So it's a study of dynamical systems. We'll look at linear systems, fixed points, chaos, fractals, complex systems. And all of this is kind of lumped together. Some of you may have heard about chaos. Some of you heard about fractals. Some of you heard about complexity theory. Though they're somewhat related, there's relations to each, but they're not the same thing. And we'll get into that as well. Now, I know you all are thinking about your grades and everything, but so we'll have a midterm exam, we'll have some homeworks, we'll have a project, and a project is going to be more of a presentation format that you'll turn in, and then there'll be a final exam. So as we go forward, we will discuss what these projects look like. Also, what the homeworks, when the homeworks are turned in, things like that. I'll make it clear to you. I know it's said here when they're due Monday, 11:59 p.m., but you know we'll adjust that according to all of our schedules. That's a good thing about having a small class. We can all kind of figure out when we want to do things. Now, with that said, this is pretty much an online class, but I do want to have a question and answer session that we can spend an hour or two, but I want to pick a day and a time that falls within everybody's schedules. I know that some of you, for the reason you're taking this online, you may already be working in some situation. So if there's an evening, for example, or even a weekend day or something like that, and we all can agree on, we'll have an hour, 2-hour question and answer session each week. But again, we'll schedule that amongst ourselves. So the grades, as you know, you've been around long enough to know how the grading system works. Here's the schedule. So this week I'm going to be going a little bit into an introduction to chaos and fractals and its history, a little bit about linear, nonlinear processes if we can get to it. Anything that we don't get to, we'll just keep pushing it down each week, because I want to make sure you get a good grasp of the concepts, the basics of this, because I want you to be conversational with this. I want you to know about it. I want you to be able to talk intelligently about it with your peers. That's the main purpose here. And in some cases, you can use it. As you'll see, as we get further and further down here, we'll actually be talking about examples of chaos use in technology. And I'm going to actually show you an example today. But we have a lot of things that we can go into. Is a big field. I encourage you to begin to look on your own, to look up papers, look up presentations. Just a lot of really interesting things going on in chaos. Some of you may remember the Jurassic Park reference. If you go back far enough, one of the characters was Ian Malcolm, played by Jeff Goldblum. And he was, I actually read the book before the movie came out, and the book goes into a lot more detail about the things he talks about with chaos than what was utilized in the movie. But in any case, it was pretty interesting. But in the end, what he was really saying is that chaos is very sensitive to changes. And that's where a lot of this comes from. So anyway, we'll get into more of that in a second. So I mentioned the reading assignments, homework, and exams. I'm also going to be using MATLAB, and I want to introduce you to it. Now, I'm not going to require that you become programmers and all that, but I'll have certain MATLAB projects, little programs that will run, that will do certain things. You could probably change some numbers and see it do various types of projects with it that I'll share with you. So what I will want you to do is have MATLAB available to you, and we're making that such that you're available to have it, to use it. Then when I provide you one of the programs, you'll be able to use it. So I mentioned chat, email. I mean, you could email me as well. And the other thing I want to tell you is just don't worry so much about grades. I want you to worry about learning the concepts. If you learn the concepts and intelligently send that back to me, what you've learned, then you'll make a good grade. And that's really what it's all about. There's some calculation, but a lot of it is really just not so specific, but more idealistic and conceptual. And I want to make sure that you get those ideas. Okay, so I think I've covered everything in the syllabus that I wanted to say. Oh, the books we've made available for you on ebook, and both of the links to these books are right here. I'm not going to try to, well, maybe let me see if I see what happens if I try to go to it. Well, this is the book by James Gleick, and it allows you to read it online here electronically. You can download it as well. This is all through our UHV account, so it's free to you to do that. And the other book is this Introduction to Dynamical Systems book. And you can see that as well. Now, these people are from the University of Maryland. I know this person, Tim Sauer. I also know James York, who's pretty famous in the chaos theory. I went to the University of Maryland for my undergraduate degree, and I got to meet these people and work with them in some of this area because I did my PhD dissertation in the application of chaos to an engineering problem. And I'll talk about that probably more towards the end of the course. But you can all feel free to not only ask me questions about it, you can Google it and search and find out probably more about it than I can remember. That's online. All right, so let's get into a little bit. So what is chaos? Interestingly enough, over now well over 100 years of research, study, analysis, modeling, experimentation, that question of what is chaos is still an open one. And not many people could give you a straight answer. There are many different types of answers of what chaos is. I like to use bounded instability. Meaning that you have an unstable process, but it doesn't blow up on you. It stays contained, but it continues to be something that, is almost random, but not quite. And we'll show some of that. So there's a scientist named Henri Poincaré, Henri, I should say, Poincaré, and around the turn of the 20th century, and he began to study the orbits of celestial bodies. And I'm going to show you one example that actually was used to do something useful. But there's the chaotic processes that are inherent in the gravitational forces within some of the celestial bodies. That's what he studied. And it really launched this whole idea of chaos and chaos theory. Then Jim York, which is much, much later in the 80s, he is credited for coining the name chaos. It wasn't called chaos before this, but in the notion of trying to describe it, define it, a lot of times it's better served to use the definition, its properties and its behavior instead of a strict definition. So let's talk about some of these properties. Well, one thing is the sensitivity to small changes. And this is something that's referred to as the butterfly effect. It's said that if a butterfly flaps its wings, say in Africa, it may launch a tornado in Kansas, right? That's the notion. But very small changes at one point can create very large changes after a time. So that's one of the hallmarks, the properties of chaotic processes. Another thing is that it is confined to a region of we'll call state space. It's not necessarily a physical space, but if you measure how it operates or its state at a given time, everything has a state, right? A state can be defined as where I'm standing, what I'm doing, how tall I am, for example. But anything you want to use to measure something, that's its state. And as you know, a state can change over time. And so the space in which you measure the changes of a particular thing over time is its state space. And the place that a chaotic system resides is within this state space, is confined to a region, but it also tends to have what's this attractor that is a fractal measure. So again, where it resides is the attractor in state space, and that attractor tends to be a fractal. Now, again, I'm throwing terms at you. I want you to just be patient as we go through this. So a lot of this will become clearer and clearer, especially when you ask questions. The other thing is as you read on your own and investigate on your own. A lot of this stuff is very interesting, so you could go down a whole rabbit trail of Googling if you want to and find out a lot about this. Then the ability of a chaotic system to be synchronized with other chaotic motion or even non-chaotic motion. So the ability to synchronize with other motion is another property of chaos. And so you put this all together, and these are some of the key properties or characteristics of chaos. Now, I want to use an example. And in 1978, NASA launched the International Sun-Earth Explorer. And this was to, as it said, explore the Sun and the Earth system. Now, as it turns out, the Earth and the Moon, its proximity, remember, so here's the Earth, and you got the Moon, and then there's the Sun, over, way over here, and it's big. And you launch a spacecraft, and the gravitational pull of each of these bodies on each other can create a complex motion. And that's what was found. Now, interestingly enough, there was a comet that was passing through the solar system, and they wanted to get this spacecraft, this is the ISEE, they wanted to get it out here to intersect and study and ultimately study that comet. But as it turned out, there wasn't enough fuel in this small device or this probe to get it there under its own power using a standard trajectory. So they utilized the complex and chaotic motion of the Earth-Moon system and sent this probe on these maneuvers that were very complex. And the interesting thing about it was that it only needed small little adjustments to its thrusters in order to put it on this trajectory. And it took a lot less fuel to send it on this motion, to take it out of, it was in a halo orbit, to take it out of this over the course of 5 years. Now, this didn't happen immediately, but over the course of 5 years, they planned and plotted so that it would intersect this comet. And that was successful, and that was the use of chaos. Here's another kind of vision of a little bit about what happened as you whirled around here, and then it began to take on this strange orbit, strange attractor, that eventually would send it off at a high rate of speed where they wanted it to go using very little fuel. And that was the benefit. And it was successful, and they studied Halley's Comet when it came through. And I believe that was in 1987. Okay, now let's talk about fractals. And let me just, pull up a bunch of fractals. Here's a bunch of them. What you're just looking at, the one that was on the slide was the Mandelbrot set, and we'll talk about that and actually do an exercise on how to generate a fractal, a Mandelbrot set fractal. But in the meantime, let's just take a look at all these different types of fractals. Now, some of these are geometric, some of them mathematical, and some come from nature. And you might be hard pressed to tell the difference if you weren't really sure. But there's a lot of beauty, but one of the key aspects of fractals is self-similarity. Okay? Now let's actually start to draw a fractal. One of the. Okay. So say I want to start with this triangle. Switch to red on me. Okay. And I'm just going to start basically cutting these triangles up into smaller ones. And as you can see, you'll never run out of triangles if you keep doing that. And you just keep doing that, and you'll continue to make more and more triangles, and eventually, actually I should have these are the empty parts. Like I should color them in, I guess. But as you begin, you'll see that you'll just keep making triangles. And this can get smaller and smaller and smaller, and as you zoom into it, it becomes infinitely large or small, depending on how you look at it. No, not large, but small. It is contained in this space here. It's contained, but there's so much going on. As you zoom further and further, you'll see an infinite number of triangles. So you're essentially getting an infinite number of objects contained in a single surface, or if you want to call it that. And you could do this in 3 dimensions too if you wanted to get really crazy with it, right? You could do the same thing. Now, so this is an example of a fractal. You could look at some others and begin, and I invite you to do that. Start looking at fractals, start looking at chaotic oscillations, read the examples that are in the books, read the chapters that are assigned, and you'll just start getting a feel. And then, because what the best thing to do is read and then come with questions. So when we set up our discussion time, we will have our questions. So how do we summarize? Well, first, we know that, chaos actually is all around us. It is defined by its properties and some of those properties are sensitive. Let me put a 1 right there. sensitive to small changes. I'm going to say lives on a strange attractor and can be synchronized. All this stuff we'll explore a little bit later. And then with regard to fractals, these are objects of fractional dimension. And we'll discuss what that means. We live in a three-dimensional world. There are dimensions 1, 2, 3, 0, 1, 2, 3. But there are dimensions in between. And those are fractals. And then also, there is this notion of self-similarity. Okay, so that's what I want you to come away with today after this discussion, these notions. And I want you to read, and I want you to investigate and be prepared with some questions. We'll work out our discussion time over email and also use Blackboard and take a look at the syllabus and let's get going. So anyway, let's end up for today. Really appreciate your time and we'll keep going.